The rate of change of any given function can be given by this formula. As you see this formula, right, we can understand this formula. The change in the function, right, divided by the ratio of, right, the change in the x, as you see. So we hope that, right, we can find average rate, average change of this function, right, when you are given any displacement on the x-axis. Of course, this is going to help us to understand the change in any problem or in any phenomenon in real world. But the better one, okay, to have a formula for the instant change. What do we mean by that? If I ask you, what would be the change at the x1 point, right? Look at that. Not just, right, the average rate between these 2 points. Can you please tell me what is the exact change at this moment, right? Or at this x value? It might be the time or it might be anything, right? I just want to know, right, the exact change, right, at that point. That would be, right, the more important than answering this question. Of course, this is going to help us, okay, to understand, to answer some question, but the instant change, okay, will be more important for me. So what would be the math tool, right, that I can use to get the answer for this question? If you look at here, right, so if this is the change formula, okay, there is no other change formula around I can use. The meaning of, right, having the meaning of knowing the change at that value, right, putting that formula x1. As you see, if I put the x1 to the here, right, since if this is the rate of change, this is the change formula, and then if I want to know, right, what is the change at the x1 value, look at that. If I assume x2 is equal to x1, that would give me the formula. But if you look at that, right, the bottom part, if you put the x1, would be the undefined, right, undefined. So I can't use this formula, right, because of the, right, the nature of this ratio. What am I going to do then? Since we have learned the limit, can I use the limit? Since limit was telling me, right, the approaching concept. As you see, if I approach to the x1 from right hand side or from the left hand side, so what I can do, I can at least, right, make this, right, the distance smaller and smaller and smaller. At the end of the day, of course, I don't want to have the zero distance, but I know that if I can close, at least I can, right, know what is going to be the change at that point. So this means, okay, I can use the limit approach, right, to get the instantaneous change, guys. That means, right, if x2, right, goes x1, I can definitely, right, write this limit in the new way. This is gonna be equal x2 minus x1, and then I'm gonna call this one instantaneous, right, the rate of change. That's perfect. So now, since I can do this, right, the operation for any x, it doesn't matter what x I use here. Instead of using the subindex, I'm just gonna put, right, the any value of x. So this is the basically, right, the difference between, right, the average rate of change and an instantaneous rate of change. As you see, limit concept, right, helped us a lot to figure out what the instantaneous rate of change will be. As you know, okay, later, okay, we will call this concept as a derivative. So now I'd like to, okay, share a nice example from your book before solving further examples. This example will be about the average rate of change in the United States population rate. So we have a model, exponential model, as you see, right? We have a model for the Hispanic population. So time is, right, the t here. So it just tells us the population at any year between, right, the 2000 and then 2050. So of course I can use this model to predict, right, the any year population for Hispanic people. But if I would like to learn, right, what would be the average rate of change, yearly average rate of change, right? To do that, I'm just gonna use, right, my average rate formula. So as you see, the rate, the change in my function, and then right the change in my time. So so here I'm just wondering, okay, what is the rate of change in the first 10 years? So I'm just going to use, right, the model. H of 10 is going to be equal to this number, and then H of 0 is going to be this number. And the bottom part is just going to be 10. If I do this, right, the calculation, I'm going to get, right, at this value. What does this means to us? Okay, what does it tell to us? So it basically tells, right, that each year, right, that the change is positive change. We have the positive change. It might be the negative change, of course, depending on what model you have. So the rate of change, right, in Hispanic population is that much, right, per year between 2000 and then 2010. Of course, you can do the same job for different years or just for the different time range. But if I ask you, right, what would be the rate of change each year, right, and not in the 10-year, as you see, right, this is the 10-year average rate of change. What if I ask you what would be the right yearly change? Then we would need to use the right instantaneous uh, rate of change formula instead of average rate of change. So we will look at, okay, more examples to see the difference between these two concepts. We give the instantaneous rate of change formula in this way: limit and when x goes x0, f of x minus f of x0 over x minus x0. And now we said that x approach x0. That means, guys, right, between the x minus x0 value, there is so small differences most of the time. So we can denote that by h. If we denote by h, x, so x is the value around x0, right? Any value can be expressed by this formula. If I use, right, this expression, new expression in the instantaneous rate of change, I would get this. When x goes x0, then, right, instead of this, I'm just going to use h. If x goes x0, h goes 0. And then here, x is equal x0 plus h minus f of x0. And then the bottom part, as you see, it is h, right? This is another version of the instantaneous rate of formula. So we can say that the second version of the instantaneous rate of change formula. So instantaneous rate of change. Okay, so most of the time we will be using, okay, either first version or the second version interchangeably. Okay, using that one, okay, will help us to figure out the operations easier than the first version sometimes. That's why, okay, we need that kind of substitution, and then we need this type of representation. Let me show you, okay, in the next example what I mean. Suppose you have a hardware store and then you sell the nails of boxes of nails, right, at $P per box, and then you want to understand the demand if you change the boxes cost to the customers. So that's why, okay, I'd like to find out the average rate of change if I increase my the price from $2 to $3. So that's why, right, the average rate of change formula I need to use from 3 to the 2. So n to the 3 minus n to the 2, I'm just going to be using this formula, 3 minus 2. So if you calculate n of 3, which will be equal 80 minus 5 times 3 squared, minus, right, the 80 minus 5 times 2 squared, and then the bottom part is just equal 1. If you calculate this one, this is going to give you negative 25. What does that mean? This means if you increase, right, the price of your box of nails this much, right, the average rate of change will happen what you sell. So you will go down, right, the 25 box of nails if you increase your, right, price of that one. So this is the average rate of change, but what would happen, right, if you sell the boxes of nails at $2? That means instantaneous rate of change, right? You need to use instantaneous rate of change formula when h goes 0. I'm going to use the second one, n2 plus h minus n of 2, right? Over, look at that, h. That's the formula I'd like to use. If I use this formula, I'm going to try to use, right, all the like limit theorem or the other things I learned before. AD minus 5 times 2 plus h squared minus AD minus 2 times 5 times 2 squared over h. I'd like to do this calculation, limit h goes 0. AD minus, right, this is going to be equal, so you need to write the first FOIL down, which is going to be 4 times 5, 20, minus 2h, 4h, 20h, and minus, right, h squared minus 5h squared. And then I had negative 80 here, and then plus 5 times 2 squared as well. So as you see, negative 80, and then 80 will go away. This will go away. I had to write the h on the bottom. So what I will have, negative 20h minus 5h squared over h. If you try to take the limit, right, when h goes 0, this would give you 0 over 0. It is one of the undefined cases we learned how to deal with. What would you do? You would just try to take the h out, limit when h goes 0, h negative 20 minus 5h over h. H will go away. Now, if you look at, right, there is no other problem, right, in my limit. When h goes 0, this guy goes 0, so it's going to give me, right, the negative 20. So as you saw, right, I took the limit, I found, right, the negative 20. What it tells me, right, that if you sell, right, at $2, the demand will decrease, right, to negative 20. That's going to be the instantaneous rate of change. So as you see, right, for a seller, it is so helpful, right, to understand this type of, right, information so that they can adjust their price, okay, to make profit or to make to adjust the demand for their products, guys. So of course, making, right, finding the limit instantaneous rate of change in this way is not practical. Later we will see a lot of different techniques, a lot of different, okay, basic approach to figure out what how we can find the instantaneous rate of change, since there will be a new concept which we call the derivative, right? And then we will have some derivative rules, okay, to handle all these instantaneous rate of change, guys.